The objective is to illustrate the research and development of neural network layer Python software models for artificial intelligence applications. The simplest deep networks are called multi-layer perceptrons, and they consist of multiple layers of neurons, each fully connected to those in the layer below, from which they receive input, and those above, which they in turn influence. The artificial intelligence, deep learning, machine learning design methodology consists of implementing and integrating linear neural networks, multi-layer perceptrons, deep learning computation. In this project, I set up my workframe environment for running in Python with Jupyter notebooks and all the relevant libraries such as NumPy and DataMath, and the code necessary to run the system based in Miniconda or Anaconda with the latest revision level of Python. The main interface to store and manipulate data for deep learning is the tensor. The goal of a supervised learning algorithm is to find a function that best maps a set of inputs to their correct output. An example would be the classification task, where the input is an image of an animal and the correct output is the type of animal. The motivation for backpropagation is to train a multi-layer neural network, such that it can learn the appropriate internal representation to allow it to learn any arbitrary mapping of input to output. The neural network algorithm corresponds to a function which, given a weight, maps an input to an output. The optimization takes as an input a sequence of training examples and produces a sequence of weights, starting from some initial weight, usually chosen at random. These weights are computed in turn. First compute using only 4. The output of the algorithm is then given a new function. The computation is the same in each step. Calculating from is done by considering a variable weight and applying gradient descent to the function to find the minimum starting at. This takes the minimizing weight found by the gradient descent. The learning algorithm can be divided into 2 phases: propagation and weight update. Phase 1 is propagation. Each propagation involves the following steps. 1. Propagation forward through the network to generate the output values. 2. Calculation of the cost. 3. Propagation of the output activations back through the network using the training pattern. Target to generate the deltas, which is the difference between the targeted and actual output values of all output and hidden neurons. There are 2 modes of learning: stochastic and batch. In stochastic learning, each input creates a weight adjustment. In a batch learning, weights are adjusted based on a batch of inputs, accumulating errors over the batch. Stochastic learning introduces noise into the gradient descent process. Using the local gradient calculated from one data point, this reduces the chance of the network getting stuck in local minima. The batch learning typically yields a faster, more stable descent to a local minimum, since each update is performed in the direction of the average error of the batch. A common compromise choice is to mini batches, meaning small batches and with samples in each batch selected stochastically from the entire data set. Phase 2 is the weight update. For each weight, the following steps should be taken. First, the weight output delta and input activation are multiplied to find the gradient of the weight. 2. A ratio percentage of the weight's gradient is subtracted from the weight. This ratio percentage influences the speed and quality of learning. The greater the ratio, the faster the neuron trains. But the lower the ratio, the more accurate the training is. The sign of the gradient of a weight indicates whether the error varies directly and inversely to the weight. The example that I illustrate in this video of the multi-layer perceptron has 4 inputs, 3 outputs, and its hidden layers contain 5 hidden units. Since the input layer does not involve any calculations, producing outputs with this network requires implementing the computations for both the hidden and output layers. Thus, the number of layers in the MLP is 2. You need to note that these layers are both fully connected. Every input influences every neuron in the hidden layer, and each of these in turn influences every neuron on the output layer. In this segment of the code, I implement a forward propagation function. It takes x as the input, calculates the hidden representation with the activation function applied, and outputs its logits. In this MLP implementation, both layers are instance variables. To see why it is reasonable, imagine instantiating 2 MLPs, net1 and net2, and training them on different data. Naturally, we would expect them to represent 2 different learned models. So we instantiate the MLP layers in the constructor of subsequently invoke these layers on each call to the forward propagation function. So the key details: first, our customized init function invokes the parent class underscore init underscore function via the super init, sparing us the pain for restarting boilerplate code applicable to all of these blocks. And afterwards, I instantiate 2 fully connected layers, assigning them to self that hidden and self that out. Not having chosen the architecture, I set up the hyperparameters and proceed to the training loop, where the goal is to find parameter values to minimize the loss function. After training, I need these parameters in order to make future predictions. In addition, I sometimes extract the parameters either to reuse them in some other context, to save the model and software models for examination in gaining scientific understanding. The algorithm is implemented by calculations involving in forward propagation through the model. When it came time to calculate the gradients, I invoked the backpropagation function provided by the deep learning framework. The automatic calculation of gradients, which is automatic differentiation, profoundly simplifies the implementation of deep learning algorithms. That is, before automatic differentiation, even small changes to complicated models required recalculating complicated derivatives by hand. Validating the equation. If the derivative rate is positive, it means that an increase in weight will increase the error. If the derivative rate is negative, it means that an increase in weight will decrease the error. Thus, we need to increase the weights. If the derivative is zero, it means that we are in a stable minimum. Backpropagation refers to the method of calculating the gradient of neural network parameters. The method traverses the network in reverse order from the output to the input layer, according to the chain rule from calculus. Here, the algorithm stores any intermediate variable, that is partial derivatives, required while calculating the gradient with respect to some parameters. Assume that we have a function y equals to f of x and z equals g y, in which the input and the output x, y, z are tensors of arbitrary shapes. I have designed several engineering prototypes based on artificial intelligence, cognitive geometric solutions. These engineering models are actual projects that benefit humanity in applications for medical, industrial, and sociological data science solutions. The engineering prototypes I have developed are mostly narrow artificial intelligence, which are able to outperform any human being, thus augmenting mankind's productivity deficiencies. However, in this mathematical artificial intelligence software model, as illustrated in this video, deals with the basic fundamentals of generating machine learning in deep science solutions. These software models form part of the artificial general intelligence. I will exercise caution as I will continue to do research and development in artificial general intelligence algorithms, always taking serious
consideration that full deployment of artificial general intelligence could potentially be mankind's last invention.